Thank you, and thanks a lot for inviting to this wonderful workshop. It's a great place. So, indeed, I'll talk about this derived CFT. The talk is largely going to be, so first of all, it's work in progress. Hopefully appear sometime this year, and there will be a lot of speculative stuff in this work, in this talk, but also some concrete computations as well. And one of the most important references here is the paper by Kapranov from 4 years ago, where he introduced the idea of derived conformal group, sort of mathematically. And then I just also mentioned this paper where they did the SUSY, the supersymmetric version of it. So I will start by some introduction and talk about conformal geometry and the twistor space and the concrete computation that we do. So first of all, what do I mean by derived symmetry? Well, in mathematics, actually, in some small portion of mathematical literature, there exists this notion of derived symmetry. Suppose you have, let's say, some variety or a scheme X, and if you talk about its symmetries, like symmetries of its complex structure, then you would be normally talking about autoequivalences of the category of coherent sheaves on this X. So that gives you your normal symmetries, and also some other stuff like multiplication by line bundles, which is sort of less relevant. But then in this sort of derived settings, one would be talking about autoequivalences of derived category of coherent sheaves. So what does it mean? Well, I see some confusion in the back. It would simply include your ordinary symmetries, like symmetries of complex structure, plus some deformations. So that would lead to the notion of this derived symmetry group. So what kind of deformations? Deformations of complex structure, or deformations, mostly deformations of complex structure of your X, plus some usually quantizations of X also appear as sort of Derived deformations, like when you turn on the B field. And the derived symmetry is usually then described by some kind of differential graded Lie algebra that unites the symmetries and deformations. Okay, so you have a complex whose, say, zeroth cohomology of that complex contains symmetries, first cohomology contains deformations, and then you can have obstructions in the higher cohomology. So then the general expectation is that if we study derived symmetries of some kind of structure S, it would be some sort of differential graded Lie algebra that unites symmetries and unified symmetries and deformations of this S. So let's speculate what could it be in physics. So in quantum field theory, more specifically. So we're looking for symmetries and deformations of something. Let's say consider usual or invertible zero-form symmetries, global symmetries of your theory. That we usually mean by that we are able to couple our QFT to some background gauge field for that symmetry. So in that case, so they couple to some principal G bundle P. In this case, this structure S that I said and referred to on the previous slide would be this principal G bundle, or like the symmetry structure. And then there's some delay between. Okay. So naturally, in this case, one would be asking what are the symmetries and deformations of this principal G bundle. Actually, we need principal G bundle with connection. let's say in simple terms, we have a background gauge field A, and then there are symmetries which are gauge transformations that preserve A, and deformations are variations of A that are not just gauge trivial variations. So for example, if the bundle is trivial and the background is 0, then the symmetries are just constant background gauge transformations, so your standard global symmetries. And then there are some deformations which are non-trivial variations. Come on, that sort of related to response of your quantum system to turning on deformation variations of turning on this background gauge field. These sort of questions of how CFT, for example, responds to turning on background gauge field for global symmetries were recently a subject of some studies in the literature. So, and of course, both symmetries and deformations in this case are determined by the current J, right? Because it determines the response of your system to the deformation. And then naturally, you would expect that the JJOP would sort of encode the whole structure, especially in a CFT where you have better control over the OP. Now, in previous example, the symmetry only acts fiber-wise on your principal bundle, so it's like internal symmetry. But you can also allow it to act on the base, in which case we're talking about the space-time symmetries, and the structure S involves some geometric data on M as well, such as Euclidean structure, in which or pseudo-Euclidean structure, in which case we're talking about Poincare symmetry. But today I'm more interested in conformal structure and conformal symmetry. Why? Well, because in this case, as I referred to previously, there's this construction by Kapranov, which sort of approaches this from a completely different angle, from derived algebraic geometry direction. And so we can sort of run that construction and then try to extract some lessons from it for physics, hopefully. So, then when I talk about conformal structure, I of course mean the metric up to rescalings, and then symmetries of conformal structure are diffeomorphisms that preserve this equivalence class. So these are your usual conformal symmetries, and then deformations are metric variations that change this class. So metric variations up to the Weyl transformations. So together, they some sort of derived conformal symmetry. And of course, both symmetries and deformations in this case are generated by your stress energy tensor. And you expect some algebraic structure to be encoded in the stress tensor OP. Of course, it's hard to decode in larger than 2 dimensions. This subject is likely related to this study of BMS algebras, or generalized BMS algebras and light ray algebras, where people basically try to encode, extract some sort of algebraic structure from metric deformations at infinity, or like that they are non-trivial asymptotically. So let me use this alternative approach by Kapranov, and let me now review that approach. So first of all, a little bit of conformal geometry. So as I said before, the conformal structure, I mean this equivalence class of metrics. So conformal manifold is just a Riemannian manifold with metric G defined up to a scale. And then diffeomorphisms are, or infinitesimal diffeomorphisms are generated by such vector fields that preserve metric up to a scale. And then the classical fact that you all know is the Liouville theorem is that in 2D, when you consider such conformal symmetries of some open set in R2, you get the Virasoro symmetry, infinite dimensional one, whereas in higher than 2D, you get this finite dimensional group of conformal symmetries. Now, the question that one can ask, and that's actually what Kapranov asked, was what happens to this infinite dimensionality once you go up in dimension? Like this jump is kind of unnatural. What's going on? Well, the answer is that this infinite dimensionality moves up in cohomological degree into the deformations of conformal structure. And then he constructed some differential graded Lie algebra. So it's a complex with Lie bracket, whose zeroth cohomology gives back the usual conformal symmetry, and the first cohomology encodes deformations. And then there's like some algebraic structure on this whole thing. And that's the derived conformal algebra. I should also say that some similar stuff have been studied in the context of holomorphic QFT in higher dimensions, where people extract some sort of higher conformal symmetries, higher versions of Virasoro algebra. But then the world of holomorphic field theories and sort of physical CFTs, they only overlap in 2D. Right? So that's why we have all this power of technology in 2D CFT, whereas in higher dimensions they move separate ways. Whereas this has been investigated to some extent in the literature, I'm interested in this world where we of course have a lot of other techniques like conformal bootstrap and so on, like numerical conformal bootstrap and some analytic results. But I'm specifically interested in the higher extensions of Virasoro in this direction. So, but nevertheless, it's still useful to analytically continue and use the holomorphic language in the following. So what do I mean by that? I want to extend the spacetime Rn to Cn and use tools of complex geometry. Of course, you cannot analytically continue the whole QFT from Rn to Cn. Right? You can go. There's this whole notion of allowable metrics, right? When you can only extend, for example, from Rn to R1, n-1, but then if you try to go further, you encounter some singularities. But I'm not worried about that because for now I'm only interested in the geometry or conformal geometry of space, and I can study real conformal geometry of Rn in terms of holomorphic conformal geometry of Cn. That's perfectly fine. And here it's also important to include Rn without a point into consideration because that's the kind of space you need to look at when you insert local operators. And when you analytically continue this sort of to Cn, then well, the origin, let's say, where insert local operator in real coordinates, it's determined by this equation. But when you analytically continue, these become complex numbers, and so instead of the 0, you get the whole Mao cone. So in the following, I will basically I'll be interested in Cn or Cn with this null cone removed, which is sort of this complexification of your real space-time where you remove the origin, where you want to insert some local operator. And then, of course, you could consider extended operator insertions and get more complicated geometries, but I'm not talking about it today. Okay, so now we're working with Cn or Cn without the null cone, viewed as a holomorphic conformal manifold. So like a holomorphic conformal manifold, now I mean complex manifold M, equipped with conformal class of holomorphic metrics. And by holomorphic metrics, I mean something like dz squared opposed to dz bar on C, because that's what you get when you analytically continue your usual Euclidean metric. And then holomorphic conformal maps are holomorphic diffeomorphisms that preserve this equivalence class. And in particular, an important example of a holomorphic conformal manifold is a non-degenerate quadric in CPN plus 1. This non-degenerate quadric is just a complexification of your sphere. And in particular, its group of conformal symmetries is just the same of is just the complexification of the group of conformal symmetries of Sn. So basically, what happens here is that the Liouville theorem, it just extends to its holomorphic version word by word. So we need to quantify the symmetries and deformations of holomorphic conformal structure. So here, a tool is actually that it's helpful. The tool that Caprano uses in his approach is the ambitwister space and ambitwister transform. So what is that? So the holomorphic conformal geometry was studied a lot by Lebrun from Stony Brook in the 80s, and in particular found that the important role is played by the space of null geodesics in F. So you have conformal manifold M, and then you have the notion of null geodesics, which is independent of conformal class of your metrics. So if you have two metrics that are just differ by rescaling, that they have the same null geodesics, and then you can consider the space of all null geodesics. Let me call it L of M. Nowadays it's called ambitwister space. I couldn't backtrack the origin of this name, but it's like here they already consider this space, but they don't name it ambitwister space. Here they already call it ambitwister space. So somewhere in between this name appeared. Maybe if someone knows, please let me know what's the origin of the name. But so here, just to remind you, or it's like what I mean by null geodesic. It's I literally take the geodesic equation and then analytically continue. Say that the time variable is now complex variable, and the tangents to your geodesic are null. So you consider space of null geodesics, and as I said, they only depend on the conformal class of your metric, not on G itself. And in particular, the knowledge. So the insight of Lebrun was that the knowledge of this null geodesics completely encodes the conformal geometry of your M. So you just can study the space of null geodesics. And in particular, this space carries a holomorphic contact structure. So contact structure is the odd dimensional analog of symplectic structure. And here you have the holomorphic version of it. So it's like you have holomorphic symplectic structure, and then you have odd complex dimensional version of holomorphic symplectic structure. So just to remind you how contact geometry works. So as I said, it's an odd dimensional analog of symplectic geometry. So let's say you have this odd dimensional manifold. Let's imagine that it's real for a moment, but or you can think of it as I'm sort of thinking of complex dimension. Then the contact structure is this codimension 1 distribution theta. So in each tangent space, you have codimension 1 subspace, such that it's maximally non-integrable distribution. I will say in a moment what that means. So in this case, it's a 2m dimensional distribution. You can introduce a contact form, which, well, here you can think of it just as a projection from the tangent bundle to the quotient of tangent bundle by this distribution. And distribution is just a sub-bundle, right? So 2m dimensional sub-bundle, you can consider the quotient, which is now a line bundle. So you have this canonical projection, and that's the contact form. So it's valued. So it's a one form valued in this line bundle. And such that, so the distribution is the kernel of this form. And the statement is that it's maximally non-integrable means precisely that if you can construct the top form from this theta, then it gives you a non-degenerate volume. Kind of like in the symplectic geometry, construct volume form from symplectic form. And then you can also have consider a vector field that's called Reeb vector field, which points in this sort of last direction, the direction that's not included in theta. And usually it's normalized such that contraction of R with the contact form is 1, and it lies in the kernel of the d theta. So as I said, we're interested in the complex version of this. So all the dimensions are complex dimensions. And the distribution is complex codimension 1. It's a distribution inside the holomorphic tangent bundle. And then the quotient is a real complex line bundle. That's actually a complex line bundle of over your x. So theta is a 1,0 form valued in this line bundle. D theta is only defined up to an ideal generated by theta, but you can always choose locally the trivialization in such a way that d theta is a 2,0 form. And this is your volume, non-degenerate volume. So in particular, it's valued as since a holomorphic volume, so it's valued in the canonical bundle times this line bundle to the m+1 first power, because you have m+1 copies of theta. And this should be non-zero section. In particular, it means that this bundle should be trivial, this tensor product. Okay, so that's a one-slide crash course on contact geometry, as well as holomorphic contact geometry. So, any questions so far? Okay, so as I advertised 2 slides ago, the space of null geodesics is in fact holomorphic contact. One can actually describe this contact structure in the following way. So suppose you have a geodesic, null geodesic, which is a point of this space of null geodesics. And then you want to characterize the tangent space to this null geodesic, which is the space of deformations of your null geodesic such that it remains null. Then you can define this distribution that gives you the contact structure by saying that gamma dot with delta gamma, the product is 0. In particular, delta gamma proportional to gamma dot is included in this, right? Because gamma dot with gamma dot is 0. It's a null geodesic. Then there's also notion of Legendrian submanifolds, which is the analog of Lagrangian submanifolds. Now, in this 2m+1 dimensional space, they are m-dimensional submanifolds such that their tangent bundle lies entirely within theta. There, m is the maximal dimension that it's possible. So if you consider a point in your spacetime X and consider all null geodesics that pass through that point, it gives you a certain subspace in L of M called Lx, the space of all null geodesics that pass through X. And in fact, it's a Legendrian submanifold in L of M. And one of the results of Lebrun is that points in M, well, okay, here is sort of obvious, this statement that points of M give you Legendrian submanifolds of L of M, but the fact is that these are, like, you don't have any other Legendrian submanifolds in L of M. And okay, here just for the, in case you wonder, give you that if the dimension of M, the complex dimension is n, then the complex dimension of L of M is 2n minus 3. In particular, if I have 3, if n equals 3, then this is also 3. And then the Legendrian submanifolds are 1 complex dimensional. And also notice that if x and y are null separated, so if there are 2 points that are null separated, then it means that the corresponding Lx and Ly intersect. So this sort of gives you intuition that the system of Legendrian submanifolds and how they intersect in your ambidextrous space encodes the data of which points are null separated, sort of. And that, in turn, encodes the data of conformal structure. So that's sort of the intuition behind this Lebrun correspondence. So his formal result is that where you have holomorphic conformal maps between two holomorphic conformal manifolds, they correspond to holomorphic contact maps of the ambitwistor spaces. And when point x1 goes to point x2, the Legendrian submanifold Lx1 goes to Lx2. So conformal symmetries in particular correspond to contactomorphisms or symmetries of contact manifold. And deformations of conformal structure of M, they correspond to deformations of contact structure of L of M.
M is a real
M, holomorphic, so complex manifold. M, yeah. So complex manifold with holomorphic conformal structure. So deformations correspond, symmetries correspond to contactomorphisms. Contactomorphisms, they are generated by contact vector fields, and here's the equation to say that psi is a contact vector field. Means that if you act with Lie derivative on theta, you get something proportional to theta. So that's like the statement that they preserve contact structure. And they are, in fact, in one-to-one correspondence with contact Hamiltonians. You get contact Hamiltonians by simply contracting contact vector field with the contact one form. Notice that this is slightly different from symplectic case, because in symplectic case, if you consider constant Hamiltonian, you get zero vector field, so it's not one-to-one. Whereas here, it's actually one-to-one. Just one of the peculiarities of contact geometry. And this in the holomorph, in our case, these symmetries or corresponding contact Hamiltonians, they are holomorphic sections of the bundle kappa over L of M. Recall that kappa was that bundle that theta is valued in.
If M is compacted, and M is also compacted.
Yes, yes. Yeah. In particular, if M is a complex 3 manifold, so complex dimension 3, L of M has also complex dimension 3. And I will describe it explicitly in our examples in a few slides. So symmetries, in other words, symmetries live in the zeroth cohomology, so in this sheaf of contact Hamiltonians. Then, sort of in the spirit of, oh yeah, and it's also not just space, it's equipped with a Lie bracket. The Lie bracket is generated by the commutator of contact vector fields. So if you have two contact vector fields corresponding to Hamiltonians H and F, you take the commutator, insert inside theta, and this is the definition of contact version of Poisson bracket of this contact Hamiltonians. So this space of symmetries is equipped with a bracket naturally, and this gives you back your usual Lie bracket on in conformal group in conformal algebra. So in this sense, the conformal symmetries are given by this. Now, it's sort of in the spirit of derived geometry, one expects to find deformations in the first cohomology. So to be more precise, deformations of contact structure theta, they can be related to deformations of the contact one form, whose kernel is this contact structure capital theta. So this is sort of the deformation theory of holomorphic contact manifolds. We can always fix the diffeomorphisms and the choice of trivialization of kappa in such a way that delta theta is a 0,1 form. So recall that theta, we assume that it's it's just a 1,0 form locally. Then deformation is a 0,1 form. At the linearized level, the fact or the requirement that it determines you the deformation of holomorphic contact structure is simply this, that it lives in the 0,1 in Dolbeau cohomology, the first Dolbeau cohomology of kappa. At the full nonlinear level, you can actually write the equation, derived equation that determines the deformations of contact structure, and it's very much like the deformations of complex structure, where you get the sort of Kodaira-Spencer equation. It's the same Maurer-Cartan equation, except you have a contact bracket here. This is the contact bracket that was introduced on the previous slide. Okay, let's just repeat that it's a contact bracket. Now, in our examples that we'll consider, all the hierarchical homology vanished, so there's no obstructions. So the fact that there's no obstructions, it means that you can actually study these things at the linearized level, the space of your deformations, and then you can solve the nonlinear equation perturbatively order by order, and you never encounter any obstructions because the hierarchical homology vanish. So then the definition that Caprano gives is this: like you simply take those called derived sections of this sheaf over L of M, and you call this derived conformal algebra. So what do you mean by derived sections? That's the complex whose cohomology computes the sheaf cohomology of kappa, basically. So for example, you could take the usual Dolbeau complex, so complex of 0, p forms valued in kappa. There would be one possible model for this derived sections. Furthermore, since this kappa is a sheaf of Lie algebras, recall that I introduced the contact bracket, gives you the Lie bracket on the sections of this sheaf. This makes the derived sections into a differential graded Lie algebra. So this step is actually non-trivial. Like you can describe different models for this DGLA. So not the most convenient one, but the most conceptually simple to introduce in this talk is the Dolbeau complex, where you simply take differential forms, 0, p forms valued in sheaf kappa, and you take the Dolbeau, the del bar, as your differential. And this gives possible model for this derived conformal algebra, because the Dolbeau differential, it's in fact, it's compatible with the contact bracket, because contact bracket is a purely holomorphic object. So del bar goes through it like in this way. So it gives you the Lie bracket, the L part here. So LA, Lie algebra, sorry. The Lie algebra part, the LA. The differential, which is the D here, and the grading, well, okay, there's grading, which is the usual form degree. But then in practice, there exist some other models, in particular something called Thom-Sullivan construction, which I'm not going to go into, but it's seems to be more convenient for certain purposes. So again, so we have this thing where the complex R-conf of M, the derived conformal algebra, whose H0 recovers usual conformal symmetries, and H1 contains deformations. And there's bracket, which also induces bracket on the cohomology, which is compatible with degree. But when you work with R-conf itself, before passing to the cohomology, in principle, it carries much more information. There's one than just the cohomology and this Lie bracket. That's like the power of working at the derived level, that you have some other data which is not visible just from purely this perspective. This, again, I remind you, this is a co-chain complex, which is defined up to quasi-isomorphisms. So isomorphisms that are chain morphisms that are isomorphisms at the level of cohomology. And that's when you work with complexes up to quasi-isomorphisms, that's what the word derived stands for always. So now let me give you some computations. In particular, let's start with a warm-up example, the 2D case, where we know everything. In this case, the space of null geodesics in C2 is just 2 copies of C. Because you have, if you are in real space, the null cone is just 2 lines. And then when you complexify, you basically have on 2 components like this one line, and then it's shifts, and the other one it shifts. And if we remove the null cone passing through the origin, that it's equivalent to removing the origin from each of these copies of C. Then the contact bundle in this case is just trivial. The contact form again is just simply dz on each copy of C. And then the conformal symmetry, if you take this sections of a trivial bundle or trivial sheaf on this space, you simply get two copies of holomorphic vector fields on C, and just gives you half of the Virasoro and half of the other Virasoro, the conjugate. Because you sort of think of these Z's as complexifications of Z and Z bar. Well, okay, in some sense. And if we are on this in the punctured case where we remove the null cone, then we recover the full Virasoro. But okay, it's central charge 0 because here I'm just working at the geometry level. Of course, once you study quantum field theory on this, you generate some non-zero central charge, which you don't see at the level of vector fields on your space. And okay, all the higher cohomology vanish in this case. So there's no deformations and no obstructions. And we know, of course, that in 2 dimensions, there are no local deformations of complex structure. Locally, every metric after a Weyl transformation can be made flat. Globally, of course, there are deformations of complex structure. That's why you have the modular space of complex structure, but that's the global phenomenon. Here, I'm talking about local things. So if I take CP2, I'm going to recover the, I guess, SL2 plus S times SL2 global conformal transformations as symmetries. And perhaps I'm going to recover. And that's it. There will be no deformations either, right? Because there's no deformation. Okay, now let me look at the. Huh? Well, from this point of view of geometry, you don't know the central charge. Right. So you can first you can ask what's the possible central extensions. You include them. Huh? No. You don't need to modify anything from this point of view. Like L of C2 is going to be the same. It's just the algebra of the vector fields on a circle with algebra, right? You cannot get central charge from that point of view. You need to consider your CFT, or you think in purely algebraically, you can classify possible central extensions, and then guess that you probably generate them once you consider quantum field theory. Well, you can look at the second Hochschild cohomology of your algebra to see what the central extensions. I mean, I'm not sure you can. I mean, where is the CFT? I'm talking about conformal symmetry. So basically, that's where the CFT is. Okay, I mean, maybe we can.
What is the
LCP2. I don't know. It's some example that would have to. but I'm going to tell you what is L of C3, because I'm mostly interested in 3 dimensions. So in this case, L of C3 is the total space of O1 plus O1 over CP1, which also coincides with the usual twistor space. Or, well, okay, twistor space where you remove sort of infinity in this case. And if I look at the C3 with the null cone removed, in this case, the L of that space is this total space, again, where I remove the 0 section of this bundle. So these are my 2 main examples that I'm interested in. The L of C3, which is the total space of this, and L of C3 without the null cone, which is the same total space with the 0 section removed. In both cases, the contact structure, the contact line bundle is given by taking O2 on the base and pulling it back to the total space. That's my kappa. And then we can compute the cohomology. Well, the zeroth cohomology in both cases is the same, and it gives you just SO5, C. So the usual complexified conformal symmetry in 3D. Now, if you look at the first cohomology, the deformations, yes. The total space, yeah. Mm-hmm. So I take O2 here and pull it back to the total. Mm-hmm. So the zeroth cohomology gives you back conformal symmetry, and the first cohomology, it's different in these 2 cases. In case of L of C3, it's certain V, which is actually an infinite dimensional representation, infinite dimensional irreducible representation of SO5. And in H1 case, it's in the punctured case, it's V plus the dual representation. So you can think of V as parameterizing regular deformations of complex structure on C3. So the deformations that are sort of non-singular everywhere. Yeah, basically, you can think of taking a metric and taking its deformations, and they're like, you can expand them in Taylor series with holomorphic coefficients, so z's to some power. And then these are sort of the regular deformations of, and take those deformations of metric up to diffeomorphisms and rescalings. So that's your regular deformations of complex structure. And V star, they are deformations that are singular along this null cone. Or if you go back to the real language on R3 without the origin, with the origin removed, they are deformations of metric that are somehow singular at the origin. And as I said, this V is some infinite dimensional irreducible representation of SO5, C. And then will higher cohomology vanish? So again, the deformations are unobstructed in this case. So at the level of cohomology, the only non-zero Lie brackets are, well, between the H0 and H0. So it just gives you your usual Lie bracket of conformal symmetry for conformal algebra. And these brackets, they just give you the representation structure of V and V dual. So just the representation data. In particular, this bracket from V to V star is 0. Well, because the H2, because it's between H1 and H1, because of the degree considerations, it would map into H2, but H2 is 0. But you can ask that question about the central charge. And in fact, it admits a central extension. You can, in this bracket, you can include a central charge in principle.
So what is the central charge?
Huh?
What is the central charge in the condition?
Well, it's like it's the one that appears in the, most likely the one that appears in the 2-point function of stress energy tensor in 3D. See.
the derived the geometry is still the central charge is the natural from the derived geometry.
No, I cannot see central charge from this point of view because it's sort of not, it's a non-geometric data. So that is something that you're supposed to sort of get from once you start studying the quantum fields that are acted on by this algebraic structure. Okay, here's that remark that you can add a central charge by hands. Now, the ambitwistor version of Penrose's transform is actually the one that relates these variations of metric with the variations of contact structure. So when you take delta theta, which is a Dolbeau form in this cohomology, and there's a certain procedure that can give you the metric variation. The procedure basically, okay, it's a little, okay, so basically you take this delta theta, which is a cohomology that lives here, and then there exists a natural map from Q times M. So Q is the space of null direction at each point. So it's null cone at each point. And the map rho, it does the following. It takes your point X on M, the null direction, and then gives you the null geodesic that goes through X in this direction. So there's this canonical map rho. So you can take delta theta, you can pull it back over here. And while in the base, it's a non-trivial cohomology class, one can check that the cohomology vanishes up here. So after you pull it back, you get del bar of something. And then this space also possesses a natural vector field that generates null flows, like at each point X and V, which is the direction, it generates you the null flow in that direction. And once you act, you can act that vector field, act with it on J, and what you get in the end is the metric variation. Oh, sorry. Contracted with P's, which are the projective coordinates on this cube. So it's a little maybe slightly difficult to catch it.
Can I ask you what your M is still complex?
Yes. Yes.
How about the metric, but is it complex, real metric or complex?
Holomorphic metric. Holomorphic. So holomorphic coefficients, and then holomorphic like things like dz squared. Mm-hmm. Yes. Yes. Oh, sorry. Because so Q. So you take 3 manifold. You take its tangent space, and which is C3, the tangent space. Inside the tangent space, there is a space of all, like you consider space of all possible directions in C3, which is CP2. And inside that CP2, there is a quadric of null directions, which is Q, which in this case is the same as CP1. So that's how it works. Okay, so let me give you some examples of this metric variation. So as I said, the deformations are given by this V in the non-punctured case, or V plus V star in the punctured case. So let's coordinatize this space, the total space in the following way. I'll have Z as a coordinate on the base in one chart of P1. And U and V will be coordinates in the fibers. Then the specific representatives of this V in Dolbeau cohomology can be written as follows, where lambda is some parameter you can You can choose any value. These all are cohomologous for different values of lambda. So in particular, what you can sort of remember is that there are these L's with 3 indices, which sort of the generalization of Virasoro's LMs, half of Virasoro LMs. So these are these cohomology. And then the V star, in the punctured case, they have slightly different form, well, very different form. In particular, whereas here these forms are supported sort of on the base, whereas here they really come from the fact that the fibers are punctured. Like the fibers in this case, the fibers of O1 plus O1, since you remove the 0 section, you really get C2 without the origin as fibers. And that's wherever this comes from. And well, just to give you some examples of these metric variations, after you run that ambitwistor transform, it's a bit, you basically can get explicit metric variations that correspond to these generators of cohomology, these cohomology elements. And then you get certain metric variations with diffeomorphisms and while transformation somehow fixed, which are some polynomials in, well, here I use coordinates on C3, which are like x0 and then x1 plus ix2 and x1 minus ix2. But, yeah. So these are coordinates on C3. If I consider, though, to say ambitwistor transform for this V star, so for these forms, it's a bit more complicated, but say element L000 gives you some metric variations. You see they're singular along the null cone, as expected, as I promised that they should be. So this sort of will be useful for connecting the formal sort of algebraic language to the actual metric perturbations that your physical system feels and responds to. Now, so here's the thing. So suppose we have we've described our DGLA. How would it act in a general conformal field theory? Well, one problem is that this derived language requires you to work with complexes, and you have some certain differential, but general CFT doesn't seem to have natural choice of differential, unless like you're some non-generic case like you're on supersymmetric theory. But general CFT doesn't have. So what's derived about it? Well, while this might not be entirely true, there are some speculations, current work in progress, which I will not go into. There may be some notion of differential. But what you can do is instead replace this DGLA by an L-infinity algebra, sort of you get in the cohomology. So which is, okay, the proper language would be to say this L-infinity quasi-isomorphic L-infinity algebra. So what is that? And then you would expect that it would actually act in a CFT. So first of all, L-infinity algebra, what is L-infinity structure? Well, it consists of so there's differential in brackets, and not only a usual binary bracket, but also higher brackets. And there's certain consistency conditions between these. And once you have a DGLA, so differential graded Lie algebra is just differential and binary bracket and no higher brackets. Once you pass to the cohomology, there's an induced structure in the cohomology where you get higher brackets but no differential.
So here is the drum side or the drum and the side.
Oh, here is just no. I'm not referring to any specific D. Just abstractly, you have like the L-infinity structure consists of the data of a complex with some differential and brackets, and there are some consistency conditions between them. Um, so once you pass to the cohomology and induce all the higher brackets in the cohomology, these, in principle, it captures the same data as initially as the DGLA itself. Well, this goes through this notion of homotopy transfer. So basically what you need to do is take your derived algebra, take the cohomology, define the maps I and P in these directions, and the homotopy map, which obey these relations that well, 1 minus IP is HD plus DH, so basically invertible. So H is like a propagator in perturbation theory, and well, sometimes people also impose additional relations that go under the name of construction. And then the brackets in the cohomology are given by sums over rooted trees. Like for example, the binary bracket is you just take cohomology, you embed it into this R, but using I, you take the bracket here and then you project back to a cohomology, and then it just gives you the usual bracket that you induce in the cohomology, but then you also get this sort of trees that give you higher structures, say the operation with 3 inputs, or say the operation with 4 inputs. Like we're currently computing these structures, but I can tell you that it's clear from the degree considerations that the bracket can only be non-trivial between these following spaces. So you take something from H0, H0, and the rest from H1, and it maps to H0, or from H0, and then the rest is from H1. And here I have n inputs, and it maps to H1. Well, okay, let me skip this for a second. We have some partial results. Basically, one can check that for C3, there are no high brackets. So basically, you just have SO5 and it's infinite dimensional irrep. But the more interesting case is really punctured case, because that's where, like for example, in 2D example, as I showed, the punctured case really is the one that recovers the full Virasoro symmetry. And in this case, we should also get higher brackets between V and V star, but they're still sort of one hard computation away. So that's like what we need to complete, and then you'll see the paper on the archive, hopefully by the end of this year. And here I also wanted to add some, at the last minute, speculation or hopes of how this would be related to the sort of TT-OPE. So we know that metric perturbations are, in physics, they're given just by, they're generated by stress energy tensor, like to the first order for infinitesimal metric perturbation. Just take T, contract it with a delta G in this way. And if you, say, have some operator inserted at the origin, you can also have that. And you can ask, well, what happens? Like this, you can think of it as sort of, you act with this metric perturbation on your operator. And then what you can do, you can assume that delta G is homogeneous of, say, degree Q. Then you can instead write delta G of 1. And due to the homogeneity property, you will extract some power of R here, coming from here. And then you can write T, the stress energy tensor at point R. Again, you can take it at point 1, at radius 1, and then dress it by the dilatation operator. Sort of in this way, what you end up is that you can think of it as follows. You act on your operator by stress energy tensor integrated along the unit spherical shell, and then you spread this using the dilatation operator, sort of integrate over the whole space. And if we define this action of sort of metric perturbation in a spherical shell as the operator Y, acting on our O, state O, then this should lead to some sort of form of action of some algebra whose structure is captured by the TT-OPE. But then actually computing the commutators or like the algebra structure here will be quite subtle because, well, because unlike in 2D, in higher dimensions, these are not symmetries, first of all. They're, of course, just deformations. And then there will be some non-trivial pole structure. And dealing with that is expected to lead sort of to this higher brackets. This is, again, a work in progress. But I don't promise this by the end of the year. But at least this part, actually, the higher brackets should be doable. And okay, well, but just some conclusions and hopes. So there's this new promising concept of derived symmetry, still at the infancy, as you can see from the talk. So I use Kapranov's notion of concrete algebra geometric proposal for derived conformal symmetry, which there seems to be a route to connected to physics. And then representation theory of L-infinity conformal algebra, the hope is it will lead to new equations and new constraints on the CFT data, kind of like you do in 2D. Maybe even something like minimal model program in higher dimensions. And it would be interesting to also investigate such things for global internal symmetries rather than space-time symmetries. And then maybe non-invertible generalizations and so on. And that's it. Thank you. And please come next year to Shanghai.
Question?
How about CFT with boundary in this setting?
Huh?
How about the CFT with boundary?
CFT with boundary.
I just ask again.
Yeah, you will have to run the similar procedure there. It's going to have also derived conformal algebra. Basically, you can consider all kinds of defects. The expectation is the same as in 2D, that you're going to break some part of this symmetry, of this structure that I've described so far in such a way that's compatible with the boundary. But like, nothing has been done about that yet. So I'm just sort of guessing here on the spot.
So what is LCN for N?
So for LCN, okay, so it's getting a bit more, it's getting more complicated as you go up in dimension, but basically you take, let me think, there's a construction. You take this space of so you look at the tangent bundle to tangent space to say a point of Cn, which is Cn again. The space of directions in that Cn is a Cpn minus 1. Inside Cpn minus 1, there's a quadratic Q of null directions, which is complexification of sphere n minus 2. So that's the space of null directions. Over that, there is a vector bundle, which is basically, it works like this. You have all directions in Cn, which is like your complex lines in Cn, and you take quotient all directions and also all shifts, and you take quotient by the tautological bundle over Cpn minus 2, and that gives you vector. So there's certain vector bundle over that CPN minus 2, which you restrict to Q, and that gives you L of Cn. So there's some. So basically, it's a certain total space of a vector bundle over the quadrant Q inside CPN minus 2. So CPN minus 1, yes. Right.
Is there any known result about the representation of L infinity conformal algebra?
Not yet, because we don't have this full structure of this algebra. And even just abstractly, the representation theory of L infinity algebras is it's not clear how much of it is known, to be honest.
Is there a further question? If not, let's thank speaker again.